Building large-scale object-oriented systems introduces a structural hazard. As the system grows, the hard-coded connections between objects fracture under the weight of their own rigidity. In traditional Java applications, objects are responsible for gathering their own dependencies. They instantiate their requirements directly to execute their business logic. When a class hard-codes its dependencies, it becomes permanently fused to them. You cannot extract that component to reuse it in a different context, and modifying one part of the system risks breaking everything attached to it. The Spring framework introduces a container built on inversion of control to solve this. Inversion of control, or IOC, is a design principle where a central framework dictates the flow of a program and the creation of objects, rather than the custom code doing it. To build reliable, enterprise-grade systems, the core responsibility of dependency creation must be stripped away from the object itself. Consider a standard architectural baseline. In the medieval-themed application, we might have a damsel rescuing knight class. This is the Java code for that class. Inside the constructor, the knight uses the new keyword to instantiate a rescue damsel quest. Because the new keyword is hard-coded, this knight is permanently bound to one specific implementation. If the system needs this knight to embark on a dragon-slaying quest, it cannot. This hard-coded instantiation makes unit testing impossible through standard injection. In a JUnit test, a standard testing framework for Java, we need to verify the knight's behavior in isolation. But because the quest is created internally, there is no mechanism to pass a test double into this class. This creates whack-a-mole bug behavior. When systems are built entirely out of these tightly bound objects, fixing an error in one class inadvertently creates new errors in neighboring classes. Hard-coded instantiation blocks the standard avenues for dependency injection. Without a point of entry for mock objects, the class remains untestable by design. Constructor injection offers a mechanical solution. This is the updated Java code for a Brave Knight class. Instead of creating its own quest, the constructor requires an abstract quest interface as a parameter. By requiring an interface via the constructor, we remove the object's knowledge of the specific implementation it will use. The knight does not know where the quest comes from or how it operates. This structure allows a developer to safely inject a mock quest using a framework like Mockito during testing. Mockito is a tool that generates dummy objects to simulate the behavior of real dependencies. We can verify the Brave Knight's logic perfectly in isolation, whereas the damsel rescuing knight remains a black box. This pattern creates an architectural paradox. If the object no longer uses the new keyword to build its dependencies, what is responsible for creating them? Constructor injection successfully decouples the object, but it only works by offloading the heavy burden of object creation to an unknown third party. That third party is the Spring application context. This schematic shows the Spring container sandbox. Isolated domain objects like the Brave Knight and the Slay Dragon quest reside inside this controlled environment. The container takes full responsibility for instantiating these objects. It then actively wires their relationships together through dependency injection, the process of supplying an object with required external resources. In early iterations, Spring achieved this wiring through explicit manual XML configuration files. Developers had to write out every connection line by line. Modern Spring development has shifted away from manual XML wiring. The framework now relies on implicit discovery and automatic wiring to connect components. The application context takes a static directory of isolated plain old Java objects, or POJOs, and transforms them into a live, fully wired enterprise application, without the classes ever being aware of it. We see this automatic wiring in action by looking at the relationship between a CD player class and a compact disk interface. The specific target dependency that needs to be injected into the player is a Beatles album. This is the Java code for the Sgt. Pepper's class. To mark it for discovery, we place the @component annotation directly above the class declaration. @component passively registers the class as a discoverable bean within the Spring ecosystem. A bean is an object that is instantiated, assembled, and otherwise managed by a Spring container. The CD player class requires the disk. Here, the auto-wanted annotation is applied to its constructor. Auto-wanted acts as an active command to the container. It forces the container to search the context for a matching bean and inject it automatically. The entire process is managed by the component scan configuration, which triggers the initial sweep across the codebase to find these annotations. By pairing component with AutoWanted, the container automates the assembly of the application graph, reducing the need for explicit configuration while maintaining type safety. While annotation-driven development feels like magic, it is actually governed by a strictly controlled sequence of runtime events. This flowchart maps the precise timeline of Bean experiences, from the moment the container discovers it to the moment it is ready for use. The container begins by instantiating the class and immediately populates its properties via dependency injection. The object then enters the aware phase. The container passes critical metadata, like the assigned bean name and the internal bean factory, directly to the object if it requires them. Finally, it hits the initialization phase. The container executes any custom init methods right before the bean is officially deployed into the live application. Exposing this granular lifecycle proves Spring operates as a rigorously controlled assembly line, giving enterprise developers exact hooks to customize object creation. Dependency injection solves tight coupling, but it has architectural limits. It fails to address the repetition of system-wide boilerplate code. Essential enterprise services like logging, security, and transaction management naturally pollute clean domain logic. These are known as cross-cutting concerns because they cut across multiple components in a system. This schematic illustrates the solution: Aspect-Oriented Programming, or AOP. AOP is the framework's mechanism for extracting these services into isolated, reusable modules. AOP declaratively applies these blanket layers of functionality over the core application at runtime. Because of AOP, the underlying domain logic executes its specific tasks without ever knowing that security checks or logging protocols are simultaneously occurring. Aspect-oriented programming is the necessary companion to dependency injection. Together, they handle the infrastructure, so the developer only handles business rules. By automating object wiring and cross-cutting concerns, the framework allows the developer to focus exclusively on business logic, while the container handles the operational complexity.